Hello to everyone that's joining us today on this webinar, and it's a good morning, good afternoon or good evening depending on where you are in the world, and I know that there are people joining us from all over the world. I'm going to be guiding you through today's webinar. My name's Nigel Ward and I'm one of the volunteers of the IET Surrey organising committee of the IET, who are the people behind today's event. Now, if you're wondering where we are, then if you've been with us before, then you will know that we have this nice little video that shows where on the world, and how fitting considering we're thinking interplanetary today, looking at where we are on the surface of our own planet. And here we are in the south of England with our home in Guildford, where today's speaker and a number of our contributors are joining from. So the topic of today's event is life on Mars. And it's an interesting topic for all sorts of reasons. We're thinking about lots of things on the global stage today, with the change of administration in the US and things beyond. Now, we could be talking about life on Mars. I hope nobody's joining for something about David Bowie and his famous theme of songs in the 1970s. I hope nobody's joining us even for the Life on Mars drama by Keeley Hawes and Robert Glenister. Or indeed, I hope no one's joining us for something about obesity and eating too many chocolate bars, because today life on Mars is something completely different. In fact, Mars is our closest planet, which has a potential for sustaining life. 3.8 billion years ago, Mars had significant volcanism, a magnetic field and water on the surface, along with a thick atmosphere. At the time when life was starting here on planet Earth, much the same things were happening on Mars. However, today, Mars is cold and dry, thin carbon dioxide atmosphere, and a very harsh surface. Now, those of you in the south of England may have felt a little bit like that the last few days with the very cold snap of weather. And if you're up further north in the UK, then I think you're certainly suffering the harsh surfaces of winter weather. But Mars is something altogether different. And today's speaker is going to be telling us all about that. He's Professor Andrew Coates, and a professor at UCL, a professor of physics and deputy director of the Mullard Space Science Laboratory. And he's heading the team called PANCAM, that is a joint ESA and Russia project, which is looking at putting a rover on Mars, and we'll be hearing all the details about that very shortly. Now, I'm sure you've come along with lots of questions in your mind, and as Andrew is telling us the story of searching for life on Mars, you'll no doubt come up with more questions. We'd be delighted if you would submit them using the Zoom Q&A facility. So if you look towards the bottom somewhere of your Zoom window, you'll find a button for Q&A. Please use the Q&A rather than the chat panel. The Q&A has our intrepid team of question wranglers. That's Mike, Samantha and Richard. They will be monitoring your questions throughout Andrew's talk. And then at the end, they will be very kindly fielding those questions to Andrew for you. Please do put your questions in there. If we towards the end, we'll come back to those questions. So that's the way to get in touch. So without further ado, I think we should bring on Andrew. Hello, Andrew, and welcome to the IET in Surrey. And we're very delighted that you're coming along today to talk to us about your topic. And without further ado, over to you.
Okay, thank you very much, and exciting to be here. So, so hopefully you can hear me, and I'm sure I'll find out if not. But so I'm going to be talking about looking for life on Mars. So I'm representing our PANCAM team. So we're building an instrument called PANCAM, or we've built that actually. It's on the rover. The rover, which is going to Mars, is called Rosalind Franklin, and we'll go into the reasons for that later on. And as was mentioned, I'm from Mars Space Science Lab, part of UCL. So we're going to talk about what Mars was like about 3.8 billion years ago and what it is like now. A bit about water and a bit about life and a bit about the ExoMars Rosalind Franklin rover. There's a few contact things there. So our website, that's our Twitter for PANCAM on the bottom left. I should say thank you very much to the UK Space Agency for funding us on PANCAM. And that's our PANCAM logo. Okay, so the rover, which is on the right-hand side here, this is a sort of golf cart sized thing. It weighs just over 300 kilograms, and we're sending it to Mars in 2022 for landing in 2023. We'll be talking about that this evening. And the instrument we have built is called PANCAM, so that stands for panoramic camera. It sits at the top of the mast there, and that's our camera system, and I will go into that in more detail. But what we're doing with this mission is drilling underneath the surface of Mars for the first time to look for signs of life. Okay, so the next slide shows us well, why we're interested in going to Mars to look for life. Well, at the moment, we only know of life on the Earth. We don't know of life anywhere else in the universe, but in our solar system, these on this slide, it shows us the top locations for life beyond Earth. So on the top left is Mars there. So that's about half the size of the Earth as it shows on the slide. So smaller than the Earth. And one of the things about being smaller is that when the planets formed, they had heat of formation. And so that heat is lost more quickly from a smaller body than it is from a larger one. So Mars lost its heat of formation more quickly than the Earth did, and that will become relevant later on. But there's other places in the solar system where there could perhaps even be life now. And so on the bottom left here, we have Europa, one of the moons of Jupiter. That's about a quarter of the size of Earth. But it's an icy satellite, and there's a liquid water ocean underneath the icy crust of Europa. And we think that's there's a possibility that, that there could even be life there now. Enceladus on the top right, so this is one of the moons of Saturn. That's only 1/25th of the size of the Earth, 252 kilometers radius. It would fit in the North Sea if you know, we don't want it actually, but if we were to bring it to Earth, it would actually fit in the North Sea. That, with the Cassini mission, we discovered that actually has a watery ocean underneath its icy crust as well. And these tiger stripes, so-called, on the bottom of the image there, the bluish colour. That is where plumes emanate from. So we discovered with Cassini that there's plumes of water and other material coming from the subsurface ocean underneath the surface of Enceladus. So we were lucky enough to be involved in the Cassini mission also. That was at Saturn from 2004 to 2017. So so I've been lucky to be involved in some of these missions. So Enceladus also has this icy surface. It has all the ingredients for life potentially there as well. So these Europa and Enceladus are really sort of top candidates for life in the solar system. Then this one, the colourful one here, this is Titan. So that's 1 over 2.5 times the size of the Earth. It's a bigger moon. It's another moon of Saturn. It orbits Saturn much further away than Enceladus does. Enceladus orbits at about 4 Saturn radii away from the planet. Titan orbits at about 20 Saturn radii. Larger radius, and that is the only moon in the solar system which has a significant atmosphere. So the atmospheric pressure there is larger than it is on the Earth. The pressure of the atmosphere is larger, but it's different substances, and it's nitrogen and methane in that atmosphere. And actually, with our instrument on Cassini, we discovered very large negative ions, and this is sort of prebiotic chemistry going on in the upper atmosphere of Titan. So we've been lucky enough to be involved in these missions and making amazing discoveries, and we're hoping that will continue with Rosalind Franklin. So Titan also has a liquid water ocean underneath its surface, but in that case the temperatures are too cold, we think, for life, but it's something where life could perhaps develop sometime in the future, and so prebiotic chemistry is what's going on there. And then towards the end of last year, actually there was a discovery at Venus, and scientists, including Jane Greaves, who led the project, she's from Cardiff University, and they discovered phosphine at Venus using telescopes on the ground. And that's interesting because phosphine is something which life could potentially be producing. There are other possibilities as well. That team is not saying they've discovered life in the clouds of Venus. Venus is really hostile place. The surface extremely hot, hot enough to melt lead on the surface. The clouds are sulfuric acid clouds, so it's a really horrible place. But nevertheless, there are possibilities perhaps for, and scientists have postulated about this in the past, for something floating in the clouds of Venus. So all of these places are a potential for life elsewhere than the Earth, but at the moment we have no proof for life anywhere other than on our Earth. So we're going to be looking for life on Mars, and future missions will look at Europa. So the European Space Agency has a JUICE mission going to Europa, being launched in 2022. Gets to the Jupiter system in 2030, goes into orbit around Ganymede, having done flybys of Europa and Callisto as well in 2032. So that's something for a little bit more in the future. But I was lucky enough to be involved in the science definition team for that, and so that's a very exciting mission, and a European mission going to look for the possible habitability of those moons of Jupiter. And with Cassini, as I say, we discovered some signs of habitability there as well. So that's been done with the Cassini mission, but I'm sure there will be future missions to both Enceladus and Titan to follow up on those results, and indeed to Venus. There are missions to Venus at the moment. This phosphine thing is an interesting result, but it's certainly not proof of anything to do with life as it stands at the moment. But so some exciting places in the solar system, and of course if we discovered life in our solar system, perhaps on one of these objects, or whether it's past or present life, that gives us a feeling for what could happen on extrasolar planets, so planets beyond our own solar system. So if you go out on a starry night and look in the sky, you see maybe 3,000 stars with the naked eye, and those are all in our Milky Way galaxy. And scientists have discovered that just about all of those actually have planets. And so the possibility of there being the right conditions elsewhere is also possible. But our own solar system is the best place to be looking for life, because we can get there. It's not easy, but you can get there with spacecraft, and that's what we're going to be doing. So I'll be talking to you about this evening. Okay, so starting off with Mars. So 3.8 billion years ago, Mars was a very different place to the place it is now. So there's water on the surface. There's lots of evidence for that, starting with the Viking missions in the 1970s, which were able to see outflow channels on the surface, particularly in the old terrain of Mars in the southern hemisphere. We'll see a bit more about that in a moment. But you can see these channels. This image here is actually from the European Space Agency's Mars Express mission, and that shows some an outflow channel here in 3D with the high resolution stereo camera, which is on that mission. There's a number of places on the surface, but this is sort of indirect evidence for water having flown on the surface of Mars 3.8 billion years ago. Another thing different about Mars is that Mars had a magnetic field. So the next image here shows the magnetic field, and so we have this is actually from the Mars Global Surveyor mission, which was at Mars roughly 1999 to 2000. This paper was 2001. What this is showing is a map of Mars. So here you can see latitude and longitude. The color scale in the background here gives you altitude. That's from an instrument called the Mars Orbiter Laser Altimeter. And so the blue colors here are relatively low regions on Mars. and then it goes through green, through yellow, and then to red and to white, which is the sort of highest areas on Mars. So you can see from that map that actually most of the high terrain is in the southern hemisphere of Mars, and the northern terrain is much lower. And then there's also this Hellas Basin here, which is also relatively low. But what's plotted over the top are these black and white contours. This is to do with the magnetic field. So this was the first time that a magnetometer had actually gone to Mars, close enough to be able to measure the magnetic field near to the planet. And it discovered this really interesting thing, which hadn't been known before. Mars has crustal magnetic fields. So the the black and the white are basically magnetic fields. There's a little bit like bar magnets. People probably remember that from school experiments and so on. So iron filings and Mars and magnets, and you can trace out the magnetic field. So we have inward and outward directed magnetic field here. So the white ones are outward directed, the white one's inward directed, and these are cusps of magnetic field. This was a big surprise from that Mars Global Surveyor region. So these regions are concentrated in that southern hemisphere. This is very old terrain. This is 3.8 billion years ago, old. We know that because of the cratering density. So the number of craters per unit area, if you compare that to the moon, and we know we've been able to date the moon from the samples brought back by the Apollo astronauts and by unmanned missions, but mainly the Apollo astronauts. So you can tell the age of that terrain, about 3.8 billion years old. So these magnetic fields are concentrated in those southern highlands, the old ancient southern highlands of Mars, and that's where those magnetic fields are concentrated. So those rocks were forming about 3.8 billion years ago, and so that gives us an idea that actually what's happened is that the rocks in forming have trapped a global magnetic field which was present at the time. So Mars does not have a global magnetic field now, but at the time, 3.8 billion years ago, it did. And that's when it trapped the magnetic field. And so this is the evidence for Mars having had a magnetic field, a global magnetic field at that time. It doesn't have that now, but so that's another big difference of Mars then compared to now. So another difference is shown on the third image here. So this is an image of a volcano on Mars, and actually this one is here on the map. It's one of the white areas, one of the highest areas on Mars, and so that is, whoops, just go back to that. And so this is the this is Olympus Mons. So this is the largest volcano in the solar system. It's about 27 kilometers high, so 3 times the height of Mount Everest, a very large feature, 600 kilometers across, but it's basically extinct. So at the time, though, 3.8 billion years ago, there was volcanism. So that would have contributed to a cycle of stuff going on. So actually, we think that Mars at that time was a bit like the Earth. And interestingly, 3.8 billion years ago to 4 billion years ago is about the time when life was developing on Earth. So conditions on Mars looked like they were about right at that time for life to have developed on Mars as well. So we're looking for the evidence for that. So we don't have evidence yet, but some of the missions are looking for that, including the one I'm talking about this evening. Okay, Mars now, on the other hand, has extinct volcanoes. There's no large-scale magnetic field, only these remnant or crustal magnetic field regions. There's a very thin atmosphere, so it's carbon dioxide rich, 7 millibars, so that's less than 1% of the Earth's atmospheric pressure. And it's a cold and dry environment. And this image actually is from the earliest rover image from Mars, showing basically, almost desert-like terrain with a couple of hills in the background, some rocks and so on, but really arid. And the surface conditions are really not nice now on Mars. So it's got this thin atmosphere, so it doesn't have any shielding from the atmosphere. The atmosphere doesn't keep the heat in as it does at Venus, for example. But on Mars, it's a very cold, dry surface. And in fact, the surface conditions are really inhospitable to life. So when I say cold, you know, on a good day on Mars, maybe 0 to 10 degrees in an equatorial region on the sunlit side, the day side of Mars. But at night, every night, it goes down to -100 to -120 degrees centigrade. So any rover or anything going to Mars has got to survive that temperature range. And of course, that temperature range is not good for life on the surface either. There's also this very thin atmosphere, which means that the ultraviolet from the sun can bathe the surface. That's not good for life. On Earth, we have the ozone layer to protect us from ultraviolet. There's nothing like that at Mars. So ultraviolet can get straight through. Also radiation from the galaxy and indeed from the sun, solar energetic particles can get through and bathe the surface with that as well. So there's radiation, there's ultraviolet, there's very cold temperatures. Not a nice place for life at all now on the surface. And this is why we want to dig underneath the surface, where conditions might be more conducive to having kept the possibility of life there if it started 3.8 billion years ago. Okay, so the next slide, there's a lot of evidence building up from the various missions which have gone in the last few years for water having been involved on the surface of Mars. This is one of them. So the NASA Phoenix mission, which went in 2008. So this is an image from that. And again, you see this sort of arid surface. This is one of the solar panels powered by solar power, this particular rover, not rover, lander. It doesn't move, but it does have this robotic arm with a shovel. And so that shovel, they could pull that along the surface and reveal what was underneath. This landed towards the North Pole of Mars, not at the North Pole, but a polar region. And on the right-hand side, we can see the trench it was able to dig. And this is sort of a few centimeters deep. And what's been done here is to superpose two images and flash them from one to another. So showing what it was first like when, keep doing that, when we had, when the subsurface material was first exposed. And so you see these areas here, these areas which then disappear. So these pictures are taken a few days apart. So as soon as you pull the thing across the surface, you reveal basically these, and then they disappear. So this is water ice crystals, which are sort of below the surface, and that sublimes into the atmosphere over a matter of a few days. So first of all, you see it, then you don't. And so that water is just underneath the surface. So some of the water which was on Mars, because we think, you know, Mars probably had flowing river channels, possibly oceans in those low areas I showed on the map. Where has that water gone? So some of it has gone underneath the surface in the form of permafrost. So this looks a bit like permafrost in the steppes and so on of Russia, it's that type of thing. So we have water crystals which then sublime into the atmosphere because of that very low pressure in the atmosphere. So the water immediately is able to sublime into the atmosphere, even at those temperatures. And this was confirmed by infrared observations of these crystals, that they're indeed water. There's other stuff in there as well, but this is the sort of first description of it. Okay, there's other evidence that's built up from other rovers. So at the moment, Curiosity, NASA's Curiosity mission, is on the surface of Mars. And one of the things they were able to find, this is a rover, so this can move around the surface. One of the things they looked at in 2014 was this region. So this, to a geologist, looks a little bit like mudstones. And so this is from mud, which was probably there 3.8 billion years ago. They were able to drill, they could drill a few centimeters with this mission, again, up to 5 centimeters with this particular mission, and analyze the material on board. And what they found with that, by doing that, was evidence for ancient lake and stream deposits in this area. And they were able to work out that this the lake, this scale bar here is 25 kilometers. So this lake is maybe 50 plus kilometers and maybe 25 kilometers in width in this region. And so this lake was probably there for a long time on the surface of Mars. And not only is it a water you know, is the main constituent, but also the pH of it, the acidity of it, was about right for potentially something to be able to survive in. So this was the first sign that habitability actually could be there on the surface as well. And so this is from the Curiosity mission from 2014. So as I say, evidence has been building up over the last few years for water on the surface of Mars. This is what the NASA rovers have been after, in particular, looking for water. Also, the European Space Agency's Mars Express was looking for water as well, using a number of different techniques. We were involved in one of the instruments on that as well, which I'll get to in a minute. But this one is a subsurface sounding radar. So this is able to look underneath the surface of Mars, up to a few kilometers underneath the surface. And in this particular region, on the left-hand side, this is a map near the southern hemisphere of Mars. And just near to there, we have this area of bright radar echoes. And these are coming from what we think is probably liquid water underneath the surface, actually, in a particular point. So liquid water about 1.5 kilometers under the surface. Whoops, about 1.5 kilometers underneath the surface here. That's where these bright radar echoes are coming from. So this is suggesting liquid water. So this is the first time this has been found. I mean, previously on Mars, you know, frozen water underneath the surface, a small amount of water in the atmosphere, and there are water clouds on Mars, you know, not due to not very high concentration of water in the atmosphere, but underneath the surface there appeared to be some liquid water as well as that solid water in the form of permafrost. This is the first time that was seen. So this is a paper in 2018 by the team associated with the subsurface sounding radar on the Mars Express mission. So Mars Express is still there and taking measurements. They looked in a bit more detail. So last year in Nature Astronomy, there was another paper about this and found 3 more lakes in the South Polar region on Mars. So very exciting, you know, liquid water. So on Europa and Enceladus, we have subsurface oceans there. And so this is subsurface ponds or lakes underneath the surface, probably mixed in with dust and so on, but nevertheless, water in the liquid state underneath the surface. So this adds to the story of water on Mars. Okay, so the water that was on Mars 3.8 billion years ago, you know, some of it went underneath the surface, both as in the form of permafrost now and also in these liquid water lakes, but some of it was lost to space. So this image here, which we did a few years ago, one of the things we do is to look at how the solar wind affects different objects in the solar system. So the solar wind is a stream of material coming away from the sun all the time. So as well as heat and light, we have this constant stream of plasma. So the 4th state of matter beyond solid, liquid and gas. This is a plasma, so superheated gas basically. So we have hydrogen and helium ions, so these are in the ionized state, and ions all the way up to iron, and then electrons as well to balance the charge. And so this flows outwards through the solar system. So when it gets to Earth and other planets, it interacts with our magnetic field, if we have one. So on the left-hand side, we have the magnetized objects. So the Earth here is very small on this picture, but our magnetopause and bow shock is upstream of the Earth here, maybe 60, 70,000 kilometers on the day side of Earth. And so that helps to protect our atmosphere. This magnetic field helps to protect our atmosphere from being pulled away by this solar wind. So the solar wind is blowing all the time, 1 million tons per second blowing outwards, and when it gets to the planets, it's doing that. So on Earth, it produces, for example, the aurora, the northern lights and southern lights. So that's one of the visible things associated with this field that you can see. And so huge amounts of energy involved, but nowhere near as much energy as involved in sunlight. Okay, so the other magnetized objects in the solar system. So Mercury is magnetized as well. This, by the way, was a surprise when this was discovered a few years ago, and the Bepi-Colombo mission is on the way there now to look at that in more detail. But nevertheless, there is a magnetic field there, much smaller scale than the Earth. And then going up in scale, there's Uranus and Neptune here, and then Saturn and Jupiter. And if you could see Jupiter's magnetosphere, it's many times the size of the sun or the full moon in our sky. So just imagine, enormous, you know, just despite the fact it's all that distance away from us, about 5 times the Earth's sun distance away from the sun, but huge magnetosphere, and so that's exciting. So on the left, so on this left-hand side of the picture, we see the magnetized objects. So all of these, the atmospheres are protected to some extent from the solar wind flow by this flow. So on the right-hand side, there's the unmagnetized objects. So Pluto, Mars, and Venus, for example, and then comets. So comets are the other visible manifestation of this field. We can see comet tails, ion tails, plasma tails, which are associated with the solar wind interaction. We've been involved in missions which have been looking at that as well. So the Giotto mission to Halley's Comet back in 1986. So I was old enough to have been involved in that, very luckily. And then also that went to another comet called Grigg-Skellerup, which gave us an interesting comparison. Also the Rosetta mission, which was going until recently and orbited with a comet as it came into the inner solar system. So some exciting cometary missions. And again, you know, the interaction with the solar wind is interesting. So Venus, Mars, and Pluto also interact with the solar wind. So you can see these objects are unprotected by a magnetic field. And so this means the atmosphere of Mars, in particular, where it's not being replenished. At Venus, we think it probably is being replenished by volcanism, but at Mars, it's not being replenished. And so that material is being pulled away by the solar wind. And it has been doing for 3.8 billion years since Mars lost its magnetic field. And that's why that atmospheric pressure is so low now. We think at the time it was probably similar to the Earth's atmospheric pressure now. Okay, so this is just an illustration of the solar wind interaction with Mars associated with another mission, a NASA mission called MAVEN. So that is there looking at the solar wind interaction, as is Mars Express as well. And we were involved in one of the instruments on that. So the sun here in the middle of the solar system, here's the solar wind streaming out from that, and an artist's impression of Mars's atmosphere being pulled away. So the solar activity goes through cycles, and so that changes the way that the interaction happens. And so that's something we look at in that field. Okay, so we think Mars 3.8 billion years ago looked a lot different. And on the left-hand side is an artist's impression of what Mars might have looked like. So it might have looked a bit like the Earth looks now, with continents, water in oceans, clouds in the sky, and so on. So at that time, that's probably what it looked like. Mars now, you know, barren, cold, etc., as I said before, and so the surface inhospitable to life. So there's this big change 3.8 billion years ago to now. As I say, 3.8 billion years ago, that's when life was starting on Earth. So if conditions were right on Earth at that time, they might have been right on Mars as well. Okay, so was there life on Mars? So it's a possibility when Mars was warmer and wetter 3.8 billion years ago at this time. And so there was some evidence announced from a meteorite, Alan Hills 84001, announced in 1996, involving the, at that time, US president, who was involved in the press conference, and NASA made this amazing announcement. But actually it was shown, and on the right-hand side, this is a scanning electron microscope picture of what were thought to be, you know, evidence of life in there. But it turns out this is to do with terrestrial contamination. This was picked up in the Antarctic, but it has to go through the atmospheres and sort of burn in the atmosphere to actually reach the ground. And so terrestrial contamination is what we think was in this meteorite. So we have to go to Mars to find out whether life actually was there at that time. And so that's what we're doing. Okay, so thinking about life, what do we need for life? So we need liquid water, that's obviously very important. And this early Mars picture again is on the right-hand side. But there's 4 things we need. We need liquid water. This is sort of recipe for life, if you like. Liquid water, we need essential elements. So there's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So that phosphine result of Venus, for example, there's the phosphorus. So we need a source of heat, and we need enough time for life to develop. And so that's what we need. We think all of those conditions were met with early Mars, as well as in the other objects which I showed you at the beginning of the talk. But Mars, you know, is the nearest place we can go to be able to look for it. So this is why we're going with the rover. So this shows the Mars Express mission. So again, European Space Agency mission. So European Space Agency has a lot going on, as well as NASA. So the Mars Express mission is one of those exciting missions, still at Mars and making measurements. Here's the subsurface sounding radar, which I mentioned before. And of course, this is how it works of bouncing radar signals back. You measure these on the orbiter and work out whether there's water underneath. So you can see water underneath the surface with the mission, you can see water in the atmosphere, and you can also see escape to space. And so this instrument here, the Aspera instrument, that's the one we were involved with and helped to calibrate and do some blackening on at our laboratory. So Mars Express also took Beagle 2 with it. This is the Beagle 2 lander here. So we're involved in this too. We did the stereo cameras on this, and unfortunately, we didn't hear from Beagle 2 on the surface, but of course a few years ago Beagle 2 was discovered. It had landed successfully on the surface, for those that remember it, but all it hadn't done was unfurl just that last solar panel to enable the radio transmission to come back to Earth. So probably our first image actually is on the surface of Mars, waiting for somebody to go and pick it up. Okay, so another exciting result from Mars Express actually is the discovery of methane on Mars, and this confirms telescopic observations, but with this spacecraft, again, European Space Agency, so the it discovered trace concentrations of methane, maybe 11.5 parts per billion. So, you know, very, very small amounts, but important enough to play an important role. And why so much excitement about methane? Well, methane should be very short-lived in the Martian atmosphere. It should be just hundreds of years. And actually, you know, it's there now. So this is surprising. We thought the Mars was basically dead. So this is being produced by something, either by geothermal activity or possibly by life. So there's some forms of life on Earth. So methanogens in swamps, for example, which produce methane. We don't think there are cows on Mars. Of course, those produce methane as well, but you know, we would have seen those. But so geothermal activity or life. So we can't tell between those two yet whether that's the case or not. So these are really tantalizing results. The Curiosity rover sees methane sporadically. So first of all, they didn't see it in 2013, then they did see it. And then in 2018, it seems to be following a cycle, the methane produced at Gale Crater where they are. And then and also oxygen was recently detected also. So so there's some recent results about that. Some exciting stuff actually happening at Mars at the moment associated with this methane. But the methane could be associated with geothermal activity, which we had thought Mars was basically dead, or potentially life, which would be an exciting result. But we don't know that yet. Some isotopic analysis needs to be done on the carbon to know that. So as for future missions, so the European Space Agency and Russia have the Trace Gas Orbiter, which went to follow up that methane result. It was launched in 2016. It got into its working orbit in 2018 at Mars, and it's been making measurements since. It landed just towards the end of the dust, sorry, it went into orbit just towards the end of the dust storm season, so the first part was obliterated by that. So far, interestingly, that has not found methane, but it's found other things in the atmosphere. So that's a result which needs to be explained. It could be that it's not sensitive enough close to the surface, and this is all happening very close to the surface, but that's we're still trying to understand that. On the right, we see the Rosalind Franklin rover. This is our rover, launching in 2022. And again, it's the European Space Agency and Russia working together. NASA have missions to Mars as well. So InSight went in 2018. You can see, by the way, these are separated by 2 years. So every 2 years you have the opportunity to launch to Mars because of the way the planets rotate and the Mars year compared to the Earth year. So every 2 years you have the opportunity, just over 2 years, you have the opportunity to launch to Mars. So InSight went in 2018. That is looking at the interior of the planet. It has seismometers on board, which are able to detect Mars quakes. So this comes when meteors come and hit the surface, and you can get a Mars quake associated with that. And using that, you can work out the interior structure on Mars. So that is not looking for life, it's looking for the interior structure of Mars. Perseverance, which was launched last year in 2020, and it's about to land in just a few weeks' time. Very exciting. We're involved in that as well, in the camera system on that. We didn't build it, but we're involved in the team, which will analyze the data. It's actually a very busy year for Mars at the moment. So last year, which was the last launch opportunity, that NASA launched their Perseverance rover. The UAE actually launched a mission to Mars as well. That's the HOPE orbiter. That will get there shortly as well. Also, China sent an orbiter and a rover in 2020. So all of these will land over the next couple of months, and or go into orbit, whichever they plan to. So the UAE one is going into orbit, and then China is going to orbit and then land as well. But on the right-hand side, this again is our Rosalind Franklin rover. This is the landed platform here, which the rover will move off, and I'll show you something about that later on. Okay, so a bit about the payload. This is the how you look for life on a planet. So this is the payload we're using to do that. So on the left-hand side, these are the context instruments on the rover. So there's PANCAM. This is our instrument. So you can see the UK flag here, of course, and we have wide-angle cameras and a high-resolution camera. There's an infrared spectrometer, which we work very closely with, a Russian instrument. There's Wisdom, which is a subsurface sounding radar. So this time on the rover, so we're able to move around the surface. This is on the rover, and this looks underneath the surface. There's Hadron, which looks at neutrons. This is actually looking for neutrons coming from cosmic rays interacting with what we think will be water underneath the surface. So H2O, the H in that means that you get a particular energy spectrum of neutrons coming off from that interaction. And so Hadron will measure that. There is also a close-up imager. So we have good scales of imaging and other measurements to get the context for what we're going to be able to do. So the key new thing about this mission is drilling up under the surface up to 2 meters. And so in the past, as I said, people have been able to drill maybe 5 centimeters underneath the surface. Inside the drill itself, there's another instrument called MARMIS. So this is a tiny visible and infrared spectrometer actually inside the drill tip. So that gets the geological context from where we get the sample from. So the sample is brought into the rover into what's called the analytical drawer from 2 meters underneath the surface. And there are 3 instruments there: micrometer, the Raman spectrometer, and the Mars Organics Mass Analyzer. So micrometer is a visible and infrared spectrometer. The Raman spectrometer is Spanish-led, but it has some UK involvement as well from Leicester University. And then the MOMA is Germany and NASA basically working on that. That is the thing which will look for organics. So this combination, we have that we're able to look at the context for the samples, look at where we're getting the samples from, and then look at the samples itself. And with these instruments, we'll be able to look at the mineralogy of what we get for the first time from 2 meters underneath the surface. And that's very important, this new dimension on Mars. Okay, so this is a little movie about the rover here. So this is looking for life on Mars. We're launching 21st of September 22. So that's the date for the diaries, just next year now. And this lands on the 10th of June 2023. We know that date already, so these are the dates for the diary. We drill up to 2 meters underneath the surface, and we have these context and analytical instruments. The rover itself, I should say, is built by Airbus in Stevenage, here is the rover, PANCAM at the top. This is the drill on the front here, the black thing. These are the Wisdom antennas. Here are the wheels, solar-powered rover, and this is an animation showing how the sample gets into the analytical drawer here. So looking with the camera system to be able to look at the grains there. But we're also looking at more remote scenes as well. Okay, so very exciting mission, and it's called Rosalind Franklin. As I say, there's a lot of UK industrial participation in this, as well as the academic involvement from ourselves and from Leicester, and other institutes around the UK as well, I should say. Quite a big team working on this, so lots of universities involved, but a big industrial involvement as well. So the prime contractor of this is actually Thales Alenia in Italy, in Turin, but Airbus were responsible and led the rover system. And I was very lucky to be able to go along to Airbus while it was being built. There was a huge thing on the side of the building saying home of the ExoMars rover. So that made me feel really good, to be able to be visiting at that time, because this is our rover, which is very exciting. Okay, so just to give you an idea of size of the rover. So this is the rover here. This is some of the PANCAM team at a meeting a couple of years ago or December 2019 in ESTEC in Holland, the European Space Technology Centre. So this is some of the team there, just to give you an idea of scale. So these are sort of passers-by, if you like. So this is the camera system sits 2 meters above the surface. And I've actually got a model of the camera system here, which I can try and show you. So this is a model of it, and we have 2 wide-angle cameras spaced by 50 centimeters. The high resolution camera, these work together, and the whole thing sits 2 meters above the surface. So we have, it gives you an idea of the PANCAM system. So why do we call the rover Rosalind Franklin? So this is after the brilliant X-ray crystallographer. She took this photograph 51, on the bottom left here, of a fiber of DNA. And this was really important in Watson and Crick's discovery of the double helix, and her work was key to that, and she probably should have shared the Nobel Prize. But this is why we're naming the rover after her, because this is very important. She did also important work on the structure of carbon and indeed viruses, so very topical. So the rover is named Rosalind Franklin in her honor. So why do we need to drill? We need to go below where these nasty things can happen. So destructive agents on Mars, I mentioned it's a very harsh surface. So getting below about 1 millimeter for the ultraviolet is important. As I say, the surface is bathed in ultraviolet of Mars. Getting below oxidants about 1 meter. And then getting below ionizing radiation, we have to get below about 1.5 meters. So I had a PhD student a few years ago working with us on looking at the radiation environment underneath the surface of Mars. And 1.5 meters is where you can start having things surviving. So his work actually is quite important. And luckily it showed that 1.5 meters was enough. So as I say, we're drilling 2 meters, and that's the first time that's been done. So we drill underneath the subsurface, get a sample and analyze it. This is our landing site called Oxia Planum. So this is a very interesting site on Mars. This is the context here. So this is between these northern sort of relatively low regions and the high southern terrain in between the two. So it's where NEC would have lapped for quite a long time. So this is one of the reasons this site was selected. There are clay-bearing rocks there, which we can see from orbiters, about 3.9 billion years old. So this is really going back in history to be able to look at this region. So it's a good place to be going with a rover which can drill to look for signs of life. There's remnants of a Fanal delta near the outlet of this Cogoon Vallis area on Mars. So that's the area which we're going to. This was selected after, a short list of places. And actually there are some engineering constraints which this audience is probably interested in terms of where you can land on Mars. You have to be somewhere fairly equatorial because of the solar power. So you have to have a relatively small angle to the sun in order to run the solar panels, to charge the batteries, etc., so that you can keep the thing warm at night using the heaters from the stored energy on board. So that's one of the engineering constraints. Another one is to do with the parachutes, to have the parachutes working for long enough in the Martian atmosphere to slow it down, bearing in mind it's only 1% of the Earth's atmospheric pressure. And there's also science. So science, of course, this is one of the interesting places to go where we have this very old area. Okay, so PANCAM, the science eyes of the Rosalind Franklin rover. So there's a look inside it, a peek inside it here. So we have the wide-angle cameras here. Each of the little camera systems has a filter wheel in front of it with 11 filters on, so we can filter out the light to look at to get a spectral analysis of the rocks. We also have a high resolution camera here, so these are the subsystems of it here, if you like, on the left hand side. So PANCAM, so electronics here, the optical bench houses the whole thing. Then we have the so-called small items. So this is the calibration target, which sits on the front to get the colors right, fiducial markers so we can get shapes right, and then a rover inspection mirror here, so we can actually look underneath the rover and see if there are any signs of rocks and so on. And this is our team, national and international, which has built this. So ourselves built the filter wheels. The wide angle cameras themselves come from Thales Alenia in Switzerland, actually. The camera, the high resolution camera, comes from our German colleagues from DLR and OHB. We provided this electronics and the optical bench, and then Aberystwyth University provided the so-called small items. But we have a science team which is international, so 9 teams working together here. This is some pictures here. So this is a science team meeting a couple of years ago, and then this actually was the camera system just before delivery. So this is the engineering team who had worked on it at the lab. So Mary Carter, our project manager, Barry Whiteside, Craig Theobald, Tom Hunt, and others here working on the camera. And this was just before it was driven around the M25 to get to Stevenage. So it literally went in this car, of course, in suitably protected in the box. We have a very clean room at ISO 5 clean room at the lab, very carefully assembled, which we'll see in a moment as well. Okay, so some of the these are the filters. So I'm so excited to be able to show this. These are the actual filters going to Mars. So we have 11 filters on each of the wide angle cameras. So as I say, these are 50 centimeters apart. That is to get very good stereo reconstruction. We can do that better than the human eyes can do because of that wide separation. So 11 filters on each of the wide angle cameras. These are the wavelengths and the widths of those. And we're basically doing with these, we're doing geology. These have been tuned to look for water-rich minerals. And we're also able to do atmospheric science with this, so looking for water vapor. So we had a student a few years ago who helped us select the filters by doing some measurements with rocks and trying to minimize the error in identifying the types of minerals which we expect on Mars. So she is now a senior academic in Scotland and still working on the team. Another student currently is working with us on the water vapor and getting the software ready for that. So she also is working with us now, just started a PhD on that. So we have a lot of students coming through working on this, which is exciting. So, and our color high resolution camera provides rock texture. So these all work together, but these are the actual filters which will be looking at the surface of Mars. So that's why it's so exciting. So some of the sort of engineering drawings here. So this is the a CAD mock-up, and so we can see the design here. So here's the filter wheel, and this is the optical bench, and then this is what it looks like, a rendering of the camera system on Mars. So this is PANCAM here, the optical bench which I showed you, this thing. So this stands on the top of the mast. Underneath it is the infrared spectrometer. So our colleague Helen Miles from Aberystwyth is responsible for this, and we had a paper about this last year in one of the IEEE journals. Okay, so so that gives you an idea. We've used PANCAM a lot in the field, and so to test out to make sure that it's going to work properly. So we have an emulator. This was built by Aberystwyth. We also did one at UCL for looking at stereo, and displayed that at the Farnborough Air Show with another student. But this this is the 3D model of a particular terrain here from one of the field trials. And we can see dip and strike has been put on this. So for geologists in the audience, if there are any, this is something where you can look at sedimentology and see how things connect to other parts of the terrain. So you can analyze that in 3D with the software which we have. So on the bottom right, we're looking at composition as well as sedimentology in the geology. So this is a principal component analysis, and we're able to separate out these different minerals which we expect on Mars. And so this is from a field trip to Iceland. So we've done a number of field trips. We summarized this in a paper in Astrobiology journal in 2017. Okay, and this just gives you a feeling for the type of data we will be able to get from Mars. And so this is a panorama from one of the field trials, which was in the Utah desert. The sky is blue, so we know it's the Earth, and actually there was a truck just off the right-hand side here, so we're not going to get that on Mars, but you know, nevertheless, it gives you an idea of the quality of the image which we'll be able to get back, these are images stitched together. It's basically a 1 megapixel camera, so but has been selected for space use, good on radiation, etc., etc. So we have to be careful about component selection. Okay, but we can stitch the images together and get this amazing scene. Okay, also a trial in the Atacama Desert. I won't go into this in detail, but again, we can look at the spectra here. This is wavelength here, and the reflectance of the rocks. Build up a spectrum and look at the different minerals. So exciting stuff. And that's the 3D image again. Okay, so this little video about the landing sequence. So I'll try and run this. So this is the landing sequence. So this is the spacecraft which is taking it to Mars, and it descends in this capsule through the atmosphere. The trace gas orbiter still there, ready to receive the signal. There's heat tiles on the front to stop it burning up in the atmosphere. Then parachutes deploy, 2 different parachutes, including the largest parachute ever to be sent to Mars, 35 meters diameter. We've had a bit of trouble with that, and so that's one of the reasons we delayed the launch. The Mars rover is released, and then retro rockets fire. This is the Russian part of this, one of the Russian parts of the mission, to stop it hitting the surface. And so it lands in Oxia Planum safely on the surface, hopefully. So that's what they call 7 minutes of terror as the thing goes through the atmosphere. So then the rover itself trundles off, well, starts to deploy. There's solar panels to get power. And then we deploy the instruments. So PANCAM is the first instrument to be deployed, so we can take a look around, see where we are. There's also navigation cameras here by industry, but this is PANCAM. And so we look around, decide which way to go, scan the Martian surface, and then eventually roll off the rover, off the landed platform. That landed platform is called Kazachuk, so that's after the Russian dance, because of the retro rockets. So we're moving across the surface. We have something called wheel walking, so that's the thing which is happening there, so we can avoid rocks. There's also some autonomy on board, again to avoid rocks. And then we select, using the context instruments, a site where we're going to drill. So this is an animation of the drilling going on. The drilling drills 2 meters into the Martian soil. So bearing in mind, 5 centimeters is all anybody has done so far. And this is the samples going into the analytical drawer. So they go inside the rover here, and we analyze that using analytical instruments. So I think in view of the time, I will stop the video there, and but basically the analysis is done inside. Okay, so this is some of the integration going on at our lab. So this is one of the technicians working on actually putting it together. And so here's the flight model of PANCAM. This is the electronics. You can see the filter wheels and the wide-angle one of the wide-angle cameras there, put together in very clean conditions. There's something called planetary protection. We don't want to take life from Earth to Mars and measure that. We have to be very careful with the cleanliness, and so we spent a lot in preparing those clean rooms to be able to do that. And of course, we're very familiar with these sort of mask type things, of course, at the moment. Okay, this is an interior picture of the of what's inside. So this may be of interest to some of you. So so here's the camera systems here. Here's the wide-angle cameras. Here is the filter wheels. So one in front of each of the 2 wide-angle cameras. So for the high-resolution camera, the light comes in here. There's a mirror. This is a focusing mechanism, and it goes onto the optical plane here. And here's some of the electronics supporting inside. Okay, so these are the filters. So we delivered PANCAM to Airbus in May 2019. It was installed on the rover in August 2019. And at that time, the European Space Agency did a press release about this and looking at our filters. these were the filters before they were put into the filter wheel. So this is into the filter wheels. And these look a little bit like contact lens cases. And so they made a comparison with that. So, and again, showing the team just before delivery. So I should say this is a huge team effort. So PANCAM on the rover here, and I'm so proud to be able to show this. So these are the flight versions of PANCAM. So the optical bench, which sits on the top of the rover here, and these are the small items which support it. And so we have that combination. And this is the flight rover undergoing some testing in Toulouse last year. It's currently in Cannes undergoing more testing before it goes back to Turin and then to Kazakhstan, which is where the launch will be from. So this is a sort of summary picture. Okay, this is installation on the mast in 2019, and Matt Gunn, which is my colleague from Aberystwyth, was in the clean room holding up a piece of paper here for PANCAM to look at. And this is the image all the way through the system. And of course it says, "Hello Mars." So that's our first light image on the rover, which we're very proud of. The optical performance is very good. We're very happy with it. And so we get basically a black and white picture, but with the colors, we can put that together to produce a color picture. So this is the launch sequence. And so these are positions of the Earth at different times. At the launch, 20th of September 2022, that is Kazakhstan time. 21st of November in the UK, of December. September is the launch, and then we get, so here's the launch to Mars, the landing 10th of June 2023, and we know what time. So Isaac Newton is in the driving seat for all of this bit. There are course corrections and so on, but basically we know when it's going to land. Okay, so just here very briefly, I think is a video. We'll see if the sound comes out on this. This is some of the engineers who worked on this. Whoops. Right, sorry, start that again.
PANCAM is a panoramic camera. Yeah, that's what it stands for.
PANCAM, this is the scientific eyes of the Rosalind Franklin rover. So we're looking at the scene on Mars, trying to do some geology, trying to do some atmospheric science.
The instrument is a fairly plain white box, essentially, but it's what's inside the box that's interesting.
We've packed as much science as we possibly can into what is basically a camera system.
We have two wide field cameras on the ends.
Stereo imaging cameras of the wax, one at each end. So on a stereo baseline of about 500 millimeters for stereo imaging and plotting of routes on the Martian surface. So looking at what's in front of the rover and working out where it can go.
So each of these wide-angle cameras has a filter wheel in front of it with 11 positions, and we can move that around to look at the different colours of the light coming from the surface of Mars. And so with that, we're able to not only build up a colour picture, but also to look at composition of the rocks, in particular looking at the light which is reflected from the rocks, to look at the minerals in them, and to look particularly for water-rich minerals, because of course we're looking for water and life on Mars.
And then we have a high resolution camera.
So the HRC light path comes in, goes, hits a fold mirror, goes through a focusing mechanism in this area, and then projects onto a sensor down at this end.
This will enable us to actually see small scale details on the Martian surface. For example, texture on rocks, or it will enable us to see single grains on the soil, and that's very important for the geological investigation of the surface.
We were PIs on the optical bench, and we produced the PIU and DC-DC converter, and they were built here.
We already delivered the hardware, so it is now in still finish in Airbus. Now they're putting all the things on the rover. The project starts since 2004. So we're talking about this is 15 years of our life is working on it.
I remember the first time I saw part of PANCAM and then got to handle some of it. And it was a pretty amazing experience to think that, you know, things that you've touched and helped with will hopefully be on Mars soon.
It would be a fantastic discovery to actually be able to find evidence for life anywhere else on the universe, and Mars is the nearest place we can look, and so our rover mission is specifically designed to do that. Okay, so I'm conscious of having overrun, so I'll just leave the last slide up. So our Rosalind Franklin ExoMars 2022 mission will provide an important new dimensional Mars drilling underneath the surface. And PANCAM, with the other context instruments, provides geological atmospheric context. So as I say, some of the contact details here, these are the institutes which worked on the hardware. We have a large team of universities working on PANCAM, including the Open Universities, St Andrews, Leicester, Aberystwyth, lots of different institutes involved, and all funded by the UK Space Agency, for which thank you very much. And I'll stop the talk there, see if there's any questions. Thank you.
That was really thorough, very good. Thank you very much, Andrew. You've given us a virtual tour of a whole planet there in a microcosm of what you're doing. Before we go on to the questions, I'm interested in the team of people that are working with you, and you seem to be a really diverse bunch of people, which is quite encouraging, I'm sure, for those people who are joining us today and might want to do something similar in the future. And how did you get to do this? What was the thing that drove you to do it?
Well, I mean, I suppose space exploration. I mean, I originally was interested in plasma physics, so as a way of solving mankind's energy problems, nuclear fusion. So I did my PhD in that, and the first degree was in that as well. I got interested in big science by doing a summer studentship at CERN years ago. So this is in the particle physics area. So I've always been interested in that sort of thing. So following the physics and going with that, and that's taken me through. So eventually got interested in plasma physics. I went to see a talk about a mission at that time, which was going to Halley's Comet, the Halley lecture in Oxford, but given by the then director of the lab, which I'm at now. And so I thought, wow, Europe is working in space, and not only that, Britain is part of it. The European Space Agency is different from the EU. It's separate and predates the EU. So Britain's a part of it, and not only that, we can get involved and do some real physics there, and we can study plasmas. So it was perfect, following the plasmas, and then getting towards working on the different missions took us eventually towards being able to work on Beagle 2, doing some imaging, and so I've been able to sort of develop the scientific things which I've been doing as with time, and so ended up as lead of this amazing camera system going to Mars. So I've been so lucky in my career, though, to have worked on so many missions, and hopefully some of the people watching today will be able to do a similar thing. So the European Space Agency is a very important source of scientific projects, and the UK Space Agency and the UK institutes play a big role in that. So we're very well placed to be able to continue doing that.
And dare I tell people looking at your CV, you've been doing this for almost 40 years?
Yeah, very nearly. So yes, I like it really, so which is quite good. And I mean, I've got the best job actually, and the best job title of anybody, Deputy Director in charge of the solar system at UCL's Mullard Space Science Lab. So the other Deputy Director is in charge of the rest of the universe. So between us, we have a coach.
But in terms of your team,
yeah.
Judging by the photographs that you showed,
yes.
That the average age is actually quite a lot lower than you or I.
Oh, absolutely, yeah. So I'm the old person looking at that proposed the instrument in the first place. But the team that are doing it and the PhD students we have coming on, working on it, and I've been very keen to involve PhD students in actually playing big roles in this project. And so that's something which we've been able to do. Some of our master's students work on it as well. So we have of course, courses at UCL to be able to do that. But yes, a diverse team, and that's important. So we have a good, our project manager is a lady, so she was responsible for getting the instrument to the spacecraft. Our contamination control engineer also, and we have quite a broad experience, and of course an international team as well, and from all different backgrounds. So yes, it's a great team to work with. Actually, all of these things are a team effort, and we really rely on the team to be able to, they're the experts, and we're just here to help really.
and I guess the idea of remote working, as you're already spanning continents, is something that's second nature.
Yes, it actually saves some travel time. So we had a science working team for the mission last week. So that, you know, I could just do that from the same room as here and make the presentations and so on about how everything is going. But it saves some time and travel. Of course, you have to move things around to be able to integrate them and get the things from different countries and integrate them together. So that's a challenge right at the moment, but nevertheless we're there. We've got the instrument on the rover, we're ready to go. And of course this is one of the projects which we're working on in the lab. There are many others as well, and so the diverse engineering team actually works on many different projects. And you know, other big ones at the moment, there's Euclid, which is going to be looking for dark energy and dark matter. Solar Orbiter, which is in orbit around the sun, with 2 instruments from our lab on it actually, and again a big involvement in all of these missions. The James Webb Space Telescope going later in this year. So there's a lot of UK activity, not only at our university but at others as well, and of course in industry as well.
That's very interesting. We've had a lot of interesting questions. I think well over 50 questions have come in. So I'm going to bring on Mike in a moment, Michael, to ask the first question. The team of questions, because so many people have put really good questions in, have grouped them together into themes. So if your question isn't asked exactly as you worded it, then hopefully the intent of your question will be covered by either Michael, Samantha, or Richard. So over to you, Michael, with the first one.
Hi there, thanks for that. We've had a few questions around the form of life that we might find, but one that we have is, how do you actually go about designing an instrument to detect a form of life that we have no idea what it looks like?
Well, yeah, that's a great question, and I mean, we're looking for building blocks of life, really. So we're looking for things like the chemistry, which I mentioned, so CHNO, and S, and looking for carbonates, and looking for you know, very, very basic building blocks, amino acids, that type of thing. In the Mars Organics Mass Analyzer, they're able to look not only at the chemical, you know, the sort of elemental abundance and the substances involved, but also look at chirality. So we can look at left-handed and right-handed molecules, one of which is used by life and one isn't. So we have to design as much as we can based on what we know about life and the way that life works on Earth. That's our best model at the moment. So you know, it's the only model which there is really. So for life anywhere in the universe, and so we're using ideas from looking at life on Earth. Of course, other types of life are possible. There's lots of ideas in science fiction about silicon-based life and things like that. But you know, we have the basic substances. Our best model is what happens on Earth, and that's the best thing we can look for in this type of experiment.
Thank you.
And Samantha, you've got the next question, I think.
Yes, hello, Professor Coates.
Hi.
The next one, there's quite a few questions around the magnetic field that was found on Mars billions of years ago. How was it lost? Someone indicated, was it due to a collision which affected the magnetic field?
Yes, great question. And actually, we're not 100% sure of the answer. I mentioned Mars lost its heat of formation more quickly than the Earth did at the beginning of the solar system because of it being smaller. And so that means that that the core could have frozen earlier. And so you lose the heat, so you lose the relative motion in the conducting you know, iron core, which produces the magnetic field. So but what we haven't got is good measurements of the heat flow at the moment, and so that would tell us whether that was the right mechanism or not. There was another theory about an impact. In fact, the one which caused that Hellas Basin in the southern hemisphere, that could have had enough energy to significantly change the system, which might have contributed to losing the magnetic field as well. So actually, the jury is out. We're not 100% sure, but we think the most likely thing is the loss of temperature. You know, that's the overriding thing, and that would be about right for about 3.8 to 4 billion years ago, and that's why it would have been lost at that time. But it's possible that the collision might have helped. In fact, there was a model in Nature a few years ago showing that indeed you could, collision could disturb the system enough to produce that change in magnetic field, and that's by somebody who does magnetic modelling at the Earth and looks at magnetic reversals on Earth, and has a good model on that. So we tried to apply that to Mars and showed that maybe the collision was important, but I think we don't know enough to show that yet. And the InSight mission actually had a heat flow measurement on it with a mole. Unfortunately, that didn't completely work, and so we still don't know the answer to that. So it's one of the things for the future. There will be lots of questions left, even if we find evidence for life on Mars, then sort of going back to that is important. And actually, to return to the previous question a bit, I guess we're looking for very primitive types of life forms, which might have come at around about that time as well. So yeah.
Sorry, just following on. I don't think you answered this, but how does presence of a magnetic field link to the life form?
Okay, so the magnetic field helps to contain the atmosphere. So if you're unprotected by a magnetic field, the solar wind can interact with the atmosphere and the charged particles at the top of the atmosphere, the ionosphere, and so particles from the ionosphere can then be pulled away. And so that, oxygen, water, everything like that will have been pulled away over 3.8 billion years. So the atmosphere has sort of trickled away over that time, and we're now left with less than 1% of the atmospheric pressure. The actual pressure does vary a bit with day and with season, but overall it's about 1% of the Earth's atmospheric pressure. And so, yes, the link is with losing the atmosphere. And so a magnetic field would have been important for having the right conditions. So the presence of the atmosphere means you have temperatures which are higher, because the atmosphere sort of blankets the planet, a bit like we have on the Earth, and indeed on Venus we have those very high surface temperatures, hot enough to melt lead. But on Mars, the atmosphere was pulled away, and so that's the reason why the magnetic field was important.
Thank you.
So conscious of time, welcome Richard. Have you got some questions for us?
Yes, thank you for a very interesting talk, Andrew. Our non-UK listeners may not know that many of the schools in the UK have gone to homeschooling. We weren't entirely expecting this to be a homeschool STEM lesson tonight, but we've got two questions coming up from 9-year-olds. So Carol and her 9-year-old daughter Ellen asks a $64,000 question, which is, why do we want to find life on Mars? And another attendee's 9-year-old son has a great follow-up question, which is, if we found signs of life, would that be good for humanity? Can wrap all that lot up with a question from David. Is there a protocol, an international protocol, of what we do with this information should we find life? Because it may have quite a profound effect on us later. So there's some cracking questions for you.
Yes, great set of questions. So yes, why do we want to know if there's life on Mars? Well, at the moment, we only know of life on Earth. We don't know of life anywhere else in the universe. As scientists, we think that, wherever there are the right conditions, that there could have been life. So what we're doing is looking for proof, looking for evidence, and trying to understand whether there indeed is life anywhere else. And so that's why we're trying to do it. It's a fundamental question. Are we alone in the universe? And so, and this is related to, thinking about the Earth. And the Earth obviously is special because it's produced us, it's produced the IET, it's produced everything which we have and everything which we know of, really in our experience. And so, why is it so special, and how special is it compared to the other planets? So one of the, of course, special things is life present here. So if we found life on Mars, or evidence for past life on Mars, I think that would have cultural implications as well as scientific ones. Life anywhere else in the solar system, on Mars or Europa or Enceladus, that would mean that life could be quite widespread throughout the universe. Wherever conditions are right, you could have life. And it takes you to the idea of, there was an equation called the Drake equation, where you're looking at the number of, he tried to work out the probability of having life like us somewhere else in the universe. And so you have to put a number of terms in that, there's star formation, there's planet formation around the stars, and then there's, does life happen does civilized life happen, all of those sorts of things. So the first few answers to that we can get from astrophysics of, what is the star formation rate? We know from recent observations that most of the planets in the Milky Way actually have planets associated with them, just about all of them. And so that increases the chances. But of course, what we can't determine with that is the last few terms of is there civilized life? But this is one of the important things. Could there be life anywhere else? And that's why we're interested in knowing that. And as for the protocols and what we would do, I mean, one thing that I didn't mention is that one of the follow-on missions to this is going to be a sample return mission to actually bring samples of Mars back to the Earth and analyze those in Earthbound laboratories. So the European Space Agency and NASA are working together on that to bring a sample back. And of course there's a possibility there of contamination of the Earth, if the life is slightly different to the Earth, and so we have to be very careful with the samples. So planetary protection, we have to worry about planetary protection with us taking life to Mars, because it would mess up our measurements, but also we have to worry about Mars life coming back to here if we bring a sample back, and could that be a big problem? So we have to make sure that we're doing the planetary protection. So that sort of answers some of it, but it's a great set of questions. Thanks. Yeah.
Thank you.
Kevin's just chipped in and said, well done to the 9-year-olds, give them a university prospectus. I think that would be a great suggestion.
Yeah.
And Michael, you pick up from there?
Yeah, so there are a few questions around the current and future Mars missions coming up as to why we had the 2 Viking missions quite a long time ago, and then there seems to be this huge gap, and then you've shown us a slide with 8 or 9 missions, and then add on to that the NASA and Elon Musk trips. What has brought about this renewed interest in Mars in the last, I suppose, 10 or 20 years?
Well, I suppose actually that since Viking, there has been a lot of interest anyway. I mean, Viking seemed to have the result that it did not find life on Mars, although there's one person who sort of queries that. But it didn't find life on Mars, but they were probably looking for the wrong thing. But since then, actually, there have been other missions. And the other thing is difficult to get to Mars. So first of all, there's every 2 years you can launch, so you can only have a certain number of missions, all of which build on the shoulders of what's been done before. And there have been accidents and difficulties. So only about 50% of the missions which are actually sent to Mars actually work because of the difficulty, in particular with landing on the surface, of getting through that thin atmosphere and landing. That is really hard. We can land on the Earth, which has got a thick atmosphere. We can land on the Moon, which has got a thin atmosphere. But in between, it is really tough. And so there are some missions which have just failed. And every now and then a mistake is made as well. So one of the NASA missions, unfortunately, there was a mix-up between the units which were used in industry and in JPL, and so the thrust was done in the wrong units, and unfortunately the thing ended up hitting the planet, which was not ideal. And so every time you have a problem, you have to wait another couple of years. So I mean, I think the interest has always been there, but it's difficult to get to Mars, and of course funding is limited. But we do have, I mean, the missions recently have sort of built one along another with the results to look at water in particular, and so the NASA missions have been looking for that in particular, looking for signs of water, and we keep discovering water on Mars in different ways, but it's all building up to a picture of what Mars was like at that time. And then, so our latest mission, what we're really boldly doing now is going to drill underneath the surface for the first time and go to the heart of the question of, was there life on Mars? And so that's why our mission in particular has a great point in this history. And then the one which will bring samples back to Earth, that will be very important as well in terms of looking for a sample. So, and actually the mission which is going here this year, Perseverance, that is going to cache samples on the surface to be brought back by a later European Space Agency and NASA mission. So that will cache mission samples to be brought back in the late 2020s. So all of this, I mean, it's a great time to be going into space exploration and space science. We have an amazing rate of discovery at the moment, but we can all make contributions, and it'd be great to see some of the younger members of the audience actually getting involved in this in either the engineering or the science, because we need both. And actually, one of the real strengths of our lab is the engineers and scientists working together on this. So as scientists, we define, you know, the science we want to do. The engineers sort of build the things to do it, and we work very closely together on that. And that's one of the things I'm proudest about our lab. And so, you know, both of those are extremely important, and both, as I say, in academia and in industry.
And I guess all of you get equally nervous on landing day too.
Oh yes, so yes, I mean, I mentioned 7 minutes of terror. I think ours is actually 6 minutes of terror, but it's terror because, and we had this with Beagle as well, but that landed, or tried to land, on Christmas Day 2003. So I was in the operations center waiting for that because we'd built the cameras and ready to take our images of Mars, and unfortunately the signal didn't come, and we found out years later that actually it very nearly worked. So it's so close, but yes, definitely terror. I mean, in all these missions, you know, we're sort of pushing the edge. The launch, of course, is dangerous in itself. On the rocket, you're basically on a you know, a missile which could explode and could have a problem, and every now and then there are launcher problems. But then apart from that, the landing is of course the next most important thing. But there's a rocket also which has to work at the end of the launch sequence to take it onto an interplanetary trajectory. So there's a few times when that hasn't worked. So all of that engineering has just got to work, and so it's exciting. On the whole of it is exciting, but particularly the last 6 minutes.
Thank you. I'll hand over to
again, there's many thanks to you, Professor Coates, for a very interesting talk. This question, there's a couple of questions around the presence of methane, which is a very interesting indicator of life. But one of the questions is, why is it so short-lived in the atmosphere? Is it because of the solar wind?
It's actually because of sunlight. So sunlight and ultraviolet breaks up. So you get photodestruction of methane over hundreds of years, which on our timescale, of course, is a long time. But on a Martian timescale, 3.8 billion years, that is a very short time. So it's sunlight which is breaking it up rather than the solar wind. Yeah.
Okay. And also, the methane, could it be from geological activity?
Yes, it could. Yeah. So and that would be interesting as well. So geological activity could indeed produce methane, and that's one of the possibilities. So distinguishing between those is difficult. So carbon 12, carbon 13, looking at that ratio is important, but it doesn't tell you everything. So we haven't had the right combination of instruments yet to be able to do that. But the Trace Gas Orbiter, the ExoMars Trace Gas Orbiter, which is now in orbit around Mars, is trying to look into that in more detail. But as I say, it hasn't actually seen methane yet, and we don't fully understand that. So this methane story at Mars is a little bit enigmatic. You know, we can't quite understand it yet because we haven't got all the measurements we need. We haven't got all the theories right to be able to explain all the observations. But Curiosity is certainly still seeing methane on the surface, but it's just not seen from the Trace Gas Orbiter, which has got sensitive enough instruments to be able to see it, you would think. So there must be something which is working within the sort of lower reaches of the atmosphere to mean that we can't see it at higher areas, but we still don't understand, and our best atmospheric scientists are onto this to try and understand. So yes, the methane is very important, and we don't fully understand it yet, I think it's fair to say.
Brilliant. Thank you. Richard, over to you.
On PANCAM, do you analyse any of the images on PANCAM on board? And when you're streaming them back to Earth, what's the latency on that round trip?
Okay, well, the whole yes, the operation sequence. Well, the round trip light time is sort of, well, one way it's between 7 and 15 minutes, depending exactly where Mars and the Earth is. So it's minutes to a couple of tens of minutes. But the way we operate the mission is to basically, at the start of a pass, we have two passes of the data relay over the orbit, over the rover every sol or day on Mars. So in the first one, we downlink the data from the previous day, analyze that, see what's gone on, uplink the commands for the spacecraft to do that the next day, and then we operate like that. So we're not operating, you know, we can't possibly operate like a computer game system or anything like that. You know, it can't be real time. The real, you know, the light time means that can't happen, but the data relay of course means that we have to pre-plan things. So we do the plan for the next day, let it do its stuff. That's why we need the autonomy on board to be able to avoid rocks and things like that, to make sure if we're sending it to drive 20 meters in that direction that it doesn't hit something, and then it sends back the information of where it is and the information which we then analyze. So all this will be done from an operation center in Turin. So we're training the teams at the moment to be able to either go and work there or work remotely. In fact, the first training stuff, of course, we're doing remotely right at the moment.
Thank you very much.
So really just to round everything off, I thought I would share something else that I found on part of the IET website, and that was about another piece of scientific research, which had concluded that there were approximately 400 billion birds on planet Earth, more than 75,000 planes, but only one superhero called Superman. So in answer to your question, it's probably a bird. And with that, we'll bid you farewell. So thank you very much for joining us.